Okay, let's talk a little bit about the Java virtual machine. So the JVM is responsible for executing machine instructions. Java is both a compiled and an interpreted language. C++, in contrast, is just compiled, and it runs natively on the target computer's platform. So when we write C++ code, we create these source code files, and they get fed into this tool called a compiler. Okay. And the job of the compiler is to translate the source code into machine instructions. The machine instructions are then put in a single file called an executable. Okay, an executable is a set of machine instructions for a given platform. For example, an Intel-based machine running a Microsoft operating system. A single machine instruction is made up of an operation and usually a piece of data. Okay, and we usually call that the opcode, is the operation that's going to be performed in that single instruction. And like I said, there's usually a piece of data that goes along with it. So some examples of opcodes might be, for example, to add. So on a particular CPU, the set of bits that determine that this machine instruction means to add might be 1010. And to subtract, well, that might be this set of bits. And different CPUs have different capabilities, but almost all of them can add, subtract, and move data around. Okay. So these might be some of the operations that are available to a CPU. Now the data that goes along with a machine instruction might include things like the contents of a register. Every CPU has a set of registers where it holds data. Might include some hard-coded data, or it might be the address of a variable in memory. The operating system feeds machine instructions to the CPU to be executed. So the CPU executes these machine instructions one at a time. The CPU understands only these machine instructions and basically follows them religiously. Whatever the operating system feeds to the CPU will carry out these operations. So when we talk about hardware, we're talking about the CPU. Then the operating system sits on top of the hardware. And again, the operating system goes and finds these machine instructions from the executable file, and it feeds them into the hardware. Now, every platform has its own compiler that produces processor-specific machine instructions. So we might have a Windows operating system with an Intel-based CPU, or a Linux operating system on an Intel CPU. But there are other ones as well. We might have a Solaris operating system with a Sun microsystem CPU. So in theory, C++ is fully portable as long as there's a compiler available for your platform. If we were going to ask the compiler to compile a statement like this, well, we have to do a little bit of arithmetic, and we also have to move some data into this variable called x. Well, on an Intel machine, okay, the add operation, the opcode might be something like this, 1010. But on a different processor, let's say a Motorola processor, the add opcode is most likely going to be completely different. Okay, because they're different. The CPUs were designed by different companies. Okay, so you should be able to take this generic C++ code, and as long as you have a compiler, the compiler will target whatever platform you want the code to run on, and C++ should be portable. However, C++ suffers from not having very rigorous standards. So for example, on a modern Intel-based Windows machine, an integer is a 32-bit number. But 15 years ago on an Intel-based machine that's running Windows, integers were only 16 bits. This variability often meant that programs would have to be ported from one platform to the next. So sometimes this was an easy job, but sometimes it was maddeningly hard. So think about a port from a 32-bit machine to, say, a 16-bit machine, where on the 32-bit machine, integers were 32 bits, and on the 16-bit machine, integers were 16 bits. Well, with a 32-bit int, we don't really have to worry too much about overflow when we're dealing with average size numbers, because the range of values was like from -2 billion to about +2 billion. But a 16-bit integer has a much smaller range, somewhere from about -32,000 to about +32,000. So we'd have to kind of get creative about how we're going to do that port. Plus, the development team would have to maintain several executables, one for each platform. And maintaining multiple versions of ported software can be challenging. So we'd have to keep track of a Windows version, a 16-bit Windows version, and maybe a 32-bit Windows version, and a 16-bit Linux version, and a 16-bit or a 32-bit Linux version, a Mac version, and so on. Now, Java source code is first compiled into bytecode, and then the JVM interprets it. Okay, so this is going to be a little bit different. When we write Java code, we still write source code files. Okay. All Java source code files end with the extension .java. And there is a compiler. We feed all the Java code into the Java compiler, which we'll learn soon. We can invoke the compiler at the command line with this command javac. The compiler, though, doesn't spit out an executable. Instead, what it does is for each .java file, it creates a corresponding .class file. And this .class file we call bytecode. Okay. Now the bytecode gets fed into this thing called the JVM. Okay, and the JVM then interprets this bytecode into platform-specific instructions. Okay, it turns out the JVM is a program that gets executed by your operating system, just like any other program. So when you run Java, or when you run a Java program, the first thing that happens is your JVM is invoked, okay, and then your bytecode is loaded into memory, and then the JVM starts to interpret that bytecode. Okay, so before we saw the job of the operating system is to feed instructions to the hardware, to the CPU. But now the JVM is a program itself. So the instructions for the JVM are being fed into the CPU, and it's the .class files, the contents of the .class files get fed into the JVM, so the JVM can interpret those into machine-specific instructions. So the bytecode in Java is very similar to machine instructions in other CPUs. So machine instructions in Java, they have an opcode, they have data, but it's specific to a virtual machine, not a real one. So the JVM has an instruction set, it has a set of registers, a call stack, a heap space, a garbage collector. It basically emulates a real piece of hardware with an operating system running on top of that hardware. And it defines this .class file format. Okay. The JVM then converts the virtual machine instructions into real machine instructions based on the platform that the JVM is running on. Okay, so the the bytecode might be made up of a machine instruction that looks like this. It gets fed into the JVM, and the JVM might turn it into a set of bits that look like this. Okay, so this is bytecode on the JVM. And this might be some machine instructions for a Intel-based Windows machine. Okay, so you might be thinking, well, doesn't this whole translation process slow things down? And the answer is yes, it does. So now you might be thinking, well, why do we do it? And the answer is we get platform independence. The JVM specification is rigorous. So if you want to call your JVM a JVM, it must behave like all other JVMs. JVMs have been created for almost all platforms, and any compiled code can run on any compliant JVM. There are no porting issues, there are no multiple versions needed. There's a consistent look and feel to all Java programs. And that's the real advantage of Java in this case. We call Java a write once, run anywhere system.